Good morning. So the mic's back up and running, so we are podcasting again, I guess. This morning I got in, I snuck downstairs into our NMR room, and I actually took some pictures of our NMRs downstairs, so you can see that there are two important parts: your computer, and then your actual magnet over here that you're going to stick your sample into. And so I also got a little bit of a closer up look at that. So the song that popped into my mind was Maxwell's Silver Hammer. So that's what I played. Okay, so I thought we would start with maybe just a quick recap of all that physics stuff that was going on. We're not too worried about the physics stuff, but we did want to have some sort of background, and so we're going to see if we can't maybe generalize that stuff as much as possible. So when we think about a nucleus, and so we're going to think about protons. So we'll say that a proton, it has a spin, and so because it has a spin, that means it's going to have a tiny magnetic field. Alright, so it's a tiny little magnetic field. And so what we've got, or what happens is if we apply an external magnetic field to our given sample, well, our little nuclei that have their own little magnetic fields are going to either align with it or against it. So we'll see that some are going to align themselves with the magnetic field, and some are going to align themselves against the magnetic field. Alright, so we call this top phase beta, and this bottom alpha. Alright, so we've got two possibilities, and so this is going to be in equilibrium. So in a given sample, what we're going to find is that some of them are in the alpha spin and some of them are in the beta spin, and so we'll have roughly proportional amounts, not quite, but almost. And so one thing we can add is that for the nucleus to align itself against the external magnetic field, that's a little higher in energy, and so what we're going to have is an energy difference we will call delta E. Now delta E depends on V naught. So the strength of our magnet certainly matters. The stronger of a magnet we have, the more delta E we can get, and the better resolution we see. Alright, so delta E is definitely dependent. And so what happens is that at some specific frequency of RF radiation excites our alpha stuff to our beta stuff. And so because of quantum mechanics, it is one specific frequency, right? Because there's going to be one specific delta E, and so only one frequency of RF radiation is going to do that excitement. So what happens is we blast this thing with a little radiation, and so our alpha nuclei are going to be converted to our beta nuclei. So everything now is going to be upstairs, aligned against, in the beta phase. Now, in this picture right here, are we at equilibrium? No, we're not at equilibrium, right? We're at equilibrium here, but we've hit this stuff with some energy, and so we've excited it, and now we're no longer at equilibrium. And that's important for us. So we'd say this picture is not at equilibrium. So what do you think is going to happen naturally? Yeah, we call that relaxation. And so what happened is those nuclei that have been converted from the alpha spin to the beta spin, they're going to relax. All right, and so what happens is those are going to, at least some of them are going to fall back down such that we are at equilibrium again. And so here we've got our return to equilibrium. And so just like we input energy to go from this state to this state, well, what's going to happen when we go from this state and then we return to equilibrium? We're going to give off energy, right? And so what form of energy do you think that's going to be? It's going to be RF radiation, right? It's going to be the same exact frequency. All right, so we return to equilibrium, and in doing so, we're going to emit RF radiation. And so our job is basically we're going to measure that emission. So whatever that emission is tells us what the delta E is, and so that's a given frequency. Of course, we don't measure that in hertz when we're looking at a spectrum. What do we measure that at? Parts per million, right? And so here we measure in ppm. And so when you look at a spectrum, that's what the ppm is corresponding to. It's telling us what frequency is emitted when after pulsing this and exciting it all, well, when this nucleus drops back down to the alpha phase, what frequency of radiation does it give off, all right? And so that's the ppm measurement we talked about. All right, so finally we ask ourselves the question, why do we see different shifts? Because we know that in the example spectrum we looked at last time, we saw this, well, there was one peak at like 1 ppm and one peak at like 3 ppm. And so we've got clearly different frequencies that are being emitted when these different protons relax. And so, again, we have our external magnetic field. So this is our nucleus, right? And so what happens is, of course, our nucleus, so our proton is involved in some bond of some kind, and so it has some electron density around it, right? And so we'll show a very crude electron cloud here. So this is our electron cloud. Now, does an electron have its own magnetic field? Yeah. It does, right? And so how does it align when we're put into this applied magnetic field? It aligns opposite. It always aligns opposite. So what happens is our electrons are going to have these tiny little magnetic fields that pretty much opposes B naught. And so if we have different protons that have different electronic structures around the molecule, are they going to have different, basically, are we going to have different amounts of electrons opposing that B naught? And so ultimately what happens is that depending on how many electrons are around the proton in question, well, they see different B naughts, right? Only different amounts of this B naught is actually going to reach the nucleus in question. And so what happens is because our electron cloud opposes B naught, we will say that it shields our nucleus from B naught. So that means that our nucleus is actually going to feel a little less of that B naught than we would expect because we have those other magnetic fields opposing. So ultimately, we see that shielding is dependent on how the electrons are arranged. And so finally, since delta E depends on how a nucleus fills B naught, what we'll find is that different nuclei have different delta E's. So ultimately they will also have different ppm. So that is our basic. This is how an NMR works in a nutshell. So each nuclei is going to fill the B naught differently, and so now it has a different delta E, which gives it a different ppm that we're able to measure. And so ultimately we see different peaks that we see end up being characteristic of specific protons in a structure. We'll talk about what those specific protons look like. Okay. So we were looking at some structures last time, and we were talking about how many signals we might expect. And so I want to do a couple more examples. So let's take a look at something just like benzene. And so benzene, of course, has a proton off of each carbon. And so, how many signals would you expect in benzene? Yeah, and so you might think, well, it seems to me that all these protons see the same they're in the same environment, right? And in fact, if we took this benzene and we rotated it 60 degrees, would we have the same picture? Yeah, and so in fact, each of these protons, it is in the same environment. And so in a molecule as simple as benzene, because of the high degree of symmetry, we only have one signal because ultimately we've only got one type of proton. Now, what we're going to find is we can start substituting our benzene. And so, for example, we could have a structure that looks like this, but we'll turn this into phenol. All right, so now we've got phenol. So we've still got protons. So Now we've only got 5 of them. And so how many signals might you expect in this case?
2.
All right, I hear 2. So clearly this is going to be different from any of the other ones, right? What about this one and this one? So clearly this one's connected to a carbon where the OH is. Is that the same case here? No, it's right. It's not, right? So here and here, these must be different. What about between here and here?
Same.
Well, this one is clearly directly across from the OH, right? It is 1, 2, 3 carbons away. Is this one 3 carbons away? It's not. It's 2 carbons away, right? And so what we see is that these are the same, right? Because they're 1 away from our OH group.
The other 2 are the same.
These will be the same because they're 2 away.
Or the opposites 1.
This is its own deal, right? It's the only proton that's all the way on the other side of the ring.
So the double bond is expected.
Remember, are those really double bonds and single bonds?
Oh no, they're just one. Like.
Right, everyone remembers the fact that the real nature of benzene is this right here. And so ultimately, all of those bonds are in fact equivalent in benzene. They're all kind of like 1.5 bonds. And so because of that, we see that in fact these are the same. Yeah, that's a good point you bring up. Because benzene is ultimately a hybrid of these 2 resonance structures, what it means is that these protons ultimately see the same amount of electron density around them. So how many signals would we see? 4. Yeah, so we'd see 4 signals. So once we break that symmetry with phenol, we see that the number of signals and the number of unequivalent protons goes up quite a bit. All right, so that's part A. We'll move on now to part B. And so, all right, so listen. So part A was about determining how many signals there will be. Part B is going to be about the area of those signals. And so we briefly talked about this, but we'll say it again. So the area of each peak is proportional to the number of H's. Now, importantly, can we ever have like a half of a proton? No, and so ultimately we want to keep in mind that it must be a whole number of H's. And so a little bit of math is required, but just the tiniest amount we're talking about. And so when we see these integrations, we want to make sure that we understand that we're talking relative numbers. So we know the relative numbers between the peaks, but we don't know the specific numbers in question. And so sometimes we might have to use the molecular formula to kind of deduce what that is. So let's look at an example. So let's say that we had a peak or a structure that looked like this. And so our x-axis we know is in ppm. So we got ppm. And so we say 1, 2, 3, 4. We'll just cut it there. Typically, a proton spectrum will go from 0 to about 10. But we'll just cut it forward here. And so let's say we see a nice peak here, right around 3. So then we'll have a bigger peak at around 1. And so in looking at this, which do you think there are more protons in? The signal corresponding to 1 or 3?
1.
Yeah, 1. And so specifically, we can have our computer integrate this for us. And so what we end up seeing, how this integrates, is we'll have this line going straight across, and then it hits our peak. And so it basically integrates it, right? Just like that. So then it keeps going across, 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 and then it integrates again. It might look something like that. So let's say that this is our baseline for our integration. We see that we get some number, say 25. And so what that tells us is that this first peak has a 25, right? That's just its integration. And so we go on over. And so here's our new baseline, and then we integrate here. And so we see that that gets an area of 75. All right, now what do you think the likelihood is that this peak right here is actually 25 protons? Is not very likely, right? And so what this means is we have a ratio here that's 25 to 75, but typically we're working with small molecules that have a lot less protons. So what other ratios could these numbers be implying?
1 to 3.
Yeah, it could be 1 to 3. What else could it be?
2 to 6.
Could be 2 to 6, could be 3 to 9. So what this is telling us is the relative amount of protons. It doesn't tell us the absolute number, but it tells us the relative. So to help us out, what we can do is maybe we know the formula of this compound. So if the formula is C5H12O, well, which ratio must be correct? How many protons are in our molecule? 12. And so which ratio adds up to 12? 3 to 9. And so what that tells us is that each peak, or the first peak is representing 3 protons, and the second peak is representing 9 protons. And in fact, this would correspond to a molecule that looks like this right here, right? So let's see, we've got one set of protons over here doing their own thing, and then we've got these 9 protons that are all equivalent. So we can see that in fact that makes sense. We do have a 9-to-3 ratio, and so that's ultimately what we're obtaining from our integration. Questions about that? Yeah, Emily?
So when we're counting protons in a sense, it's only the H's out of protons.
Yes. And specifically, we're focusing in here on 1H NMR spectroscopy, and so we're only talking about the proton nuclei. Yeah, that's the only signals we're obtaining. Yep. Okay. From last class, why is carbon NMR not used as much? Yeah, is the carbon-12 nucleus active? It is not, unfortunately. So this is why we really focus in on protein. Okay, so that's part B. And we're going to get lots of practice with this. I think on Monday we're going to go over lots of examples. And then in lab next week, as well as the week after that, you're going to see tons of examples of interpreting spectra like this stuff. All right, so part C is chemical shift. So from our little review, we can see that chemical shift depends on how shielded. And so what's doing the shielding?
Electron.
Yeah, so shielding by electrons in nucleus is. So there's going to be 2 main effects that we talk about. So first off, there's going to be inductive effects. And then there's going to be pi bond effects. And so importantly, when we talk about an NMR spectrum, when we go this way, are we becoming more shielded or more de-shielded? More de-shielded, right? So if we shift this direction, that means we're becoming more de-shielded, and there is less electron density around our atom, or our protons in question. Okay, so first off, let's talk inductive effect. And so this one is, I think, pretty straightforward. So the inductive effect is going to be based on electronegativity. And so what we see, we'll show some trends, and I think it'll be pretty obvious what's going on. So we could have this molecule. We could have this molecule, and finally we'll just have methane, just like that. And so, these protons, so we're looking at these methyl groups in all cases, right? We're thinking about what the shift would be of these methyl groups. So what do you think is going to be the most de-shielded protons in this case? The ones on the left or the ones on the right? On the left, right? Because we know we've got a strong dipole pulling in that direction. So that fluorine is sucking that electron density this way, which leaves those protons on that molecule pretty de-shielded, and about as de-shielded as it's going to get just from an inductive effect. And so what we end up seeing is that on the left side we are more de-shielded, and that ultimately results from more electronegative atoms attached. And so in terms of chemical shift, we see this would be about 4.3 ppm, would be about 3.5, 2.7, and then finally just methane itself comes in around 1 ppm. And so as we increase the electronegativity of the atom attached, we can see we're de-shielding our protons more, and so they shift more downfield. All right, so furthermore, the more electronegative atoms we have on there, the more de-shielding takes place. place, and so we can have, let's say, chloroform, and we could have dichloromethane with its 2, and then we could have just chloromethane. And so which protons do you think are going to be the most de-shielded? Again, it's going to be the one on the left, right? Because in the picture on the left, we have 3 electronegative atoms pulling away that electron density. And so, in fact, the shifting that we see in a molecule like chloroform is pretty intense. So this comes in around 7.3 ppm. That's way downfield. And then the less there are, the less de-shielding there is. And so then we can see that going left to right, they become more shielded, and thus they come back to the right side on our spectrum. All right, so the electronegativity of the atom matters, and so does the number of electronegative atoms attached. Finally, let's look at this example. So let's say we have a methyl group, and a CH2, a CH2, and a Cl. Now, how many signals would we expect?
3.
Yeah, we'd expect 3 signals. Those are all going to have different chemical shift, and we're going to see 3 obviously different peaks in this spectrum. So which do you think are going to be shifted downfield the most? These or these? Definitely the ones on the right? And so because they're experiencing that inductive effect more because they're closer to the chlorine. So the shift that we see for this CH2 right here is going to be about 3.3 ppm. And as we move further away, we see that there is less of an inductive effect. So then we see 1.6 ppm, and over here this ends up being around 0.9 ppm. And so a lot of this stuff I think you could sort of draw from what you've seen with electronegativities in the past, where you can see that in the NMR spectra that we will be interpreting, we see similar trends as we've discussed before. All right, so that's electronegativity. We'll move on now to pi bond effects. So these are a little more, obviously they're a little more interesting, I think, than the electronegativity effects. So let's compare 3 molecules. We use ethane, and we'll use ethene. What's the common name of ethene? Ethylene. And so we also show ethine. What's the common name of ethine? Acetylene. All right, so we've got different hybridization of our carbons. So this one's going to be sp3, sp2, sp. So we've sort of seen this table before, right? Because we've talked about S character. And so which has the most S character, sp3 or sp? Definitely sp, right? Because in that case, S is making up 50% of the hybrid orbital. So we're going to have 50% S character here, and then 33% here, and 25% here. And so as we go down the table, do we see increasing electronegativity from those orbitals or decreasing electronegativity? Increasing, right? And that's because S orbitals being close to the nucleus are just more electronegative orbitals. And so as we move down our table, we see more electronegative orbitals. And so when we think about those protons, well, if this carbon right here has a really electronegative orbital that's pulling electron density away from that hydrogen, we would expect to see more de-shielded hydrogens, right? So let's see what the trend ends up being. All right, so over here we'll put our little delta. And so what does delta stand for? That's our ppm. So anytime you see that, that's just our symbol for ppm. So with ethane, we've kind of seen this before. We see a shift of about 0.8 to 1.7. So all that stuff tends to be on this side, down around 1. And so we get to ethylene, and in fact what we see is this jumps up to somewhere around 4.5 to 6.5. And so depending on where the shift is specifically, it depends on that structure in question. So it can vary quite a bit. And so where do you think acetylene is going to be? Just toss a number out. 8. Acetylene is about 2.5. Which might ask us, or lead us to ask the question, why on earth is acetylene being weird? And so we're going to talk about that for a second. All right, so why is it weird? That is our question, and so fortunately I'm qualified to answer that. So the answer is anisotropic effects. So let's think about what's really going on when we have pi bonds. All right, so pi bonds, are they held more tightly or less tightly to our atom or to our molecules? Pi bonds are held less tightly, right? They're not held between the nuclei. They're extended up, and so they're held less tightly. So we have pi bonds that are held less tightly. And so what happens is they're held so not tightly that when we put them in these applied magnetic fields, they begin to kind of circulate and dance around a little bit. So the pi bonding electrons begin to, let's say dance, I like that. But maybe we'll just add in circulate so we sound professional. All right, so they begin to dance around a little bit. So they dance in a circle, and so what that means is, guess what? They're going to have their own magnetic field from this, right? Because we have charges, and they are now literally circulating. And so what happens is this dancing or this circulating is going to lead to a new magnetic field. Lots of magnetic fields. In my notes I wrote, good grief. All right. The presentation wasn't good on it, but the thought was there. All right, so good grief. Let's talk about why we see what we see. So I'm mainly showing this because I think it's really cool. All right, so let's think about what happens. Let's start with ethylene. So you don't need to be able to draw these pictures from scratch, but I just kind of want to explain why we see what we see when we have pi bonds. And so when we have, and I'm going to draw big. So we have an applied magnetic field. Let's have our magnetic field go this way. And so what's going to happen is our acetylene is going to orient itself like this. So you might ask yourself, why does it orient itself like this? Well, those pi bonding electrons that are now circulating and have their own magnetic field, how does the magnetic field of electrons line up with the applied magnetic field? With or against? Against. And it still wants to be against. And so we kind of can imagine this magnetic field going straight up the middle of our acetylene. And so that means that we're going to end up with a magnetic field that looks something like this. And so it's going to be going in this direction, because in the middle of our molecule, it wants to be going against. I have conflicting arrows. It's going to go against our magnetic field. But are the protons in the middle of our molecule? No, they're not. They're on the outside. And so in reality, the pi bonding electrons, when that magnetic field either opposes or adds to the applied magnetic field, what are the protons feeling? Are they feeling less B naught or actually more B naught now? They're actually feeling more B naught in the case of acetylene. So our protons here are going to be what we would consider.
Wait, but isn't that ethylene?
Yeah, what did I say?
You said acetylene.
Oh, I meant ethylene. Yeah, I just misspoke. So what we see is we end up with extra D-shielded electrons in ethylene. And so that downshift that we saw from 4.5 to 6.5, well, certainly some of it has to do with the electronegative orbitals, but some of it is also this anisotropic effect, where the magnetic field of our pi bond is going to line up such that the middle of our molecule opposes B naught, but that just means that our magnetic field is actually going to add to B naught for our protons. And so considering that acetylene, we see more of an upfield shift compared to ethylene, well, what do you think is the reason for that? Do you think that the magnetic field is ultimately going to add, or do you think it's going to shield it more? It's going to shield it more, and so let's see how acetylene lines up, and so ultimately this will explain why we see what we see. So we've got our B naught, and so what happens is our acetylene ends up lining up, and it's because of the extra pi bonding density, like this. And so again, we're going to have a picture where the middle of our molecule is going to oppose the B naught. And so that means that they're going to be going in this direction. And so unlike in ethylene, these pi bond shielding, is that arrow, is this new magnetic field going, at least around the protons, is it going with B naught or against B naught? It's opposing B naught, right? So here we've got an extra magnetic field that is going with B naught, and so we see lots of de-shielding. In this picture, our magnetic field, when it hits the protons, is now opposing B naught, and so what we end up seeing is extra shielding. And so ultimately, we see a shift of about 2.5 ppm for acetylene, but more like 5.5 ppm for ethylene. And so ultimately, it's this extra magnetic field that in one case, you can see is adding to B naught. In this other case, is going against B naught, at least where the magnetic field is hitting our protons, right? So here our protons are on the outside. Here our protons line up on the inside. So again, you don't have to be able to paint this picture, but I just think it's a kind of a cool little story. Why do we see the shifting in triple bonds that ends up being different from the shifting in double bonds? So one more case. We'll talk about benzene. And so our benzene is going to ultimately line up and look kind of this. And we're just going to draw two of our protons. And so again, we'll have a B naught. It goes this way. We'll see a magnetic field where the middle of the molecule opposes B naught, as it is wont to do. And so is benzene, you think, going to be more like ethylene or more like acetylene? It's going to be more like ethylene, right? Because when we look at these protons, we can see that they're experiencing this extra magnetic field in the direction of B naught, right? So acetylene is the weird case. Acetylene, we've got protons that are experiencing the extra magnetic field against B naught. Ethylene, we can see the magnetic field as it is near our protons is with B naught, and so it's the same case here. And so do you think we're going to see shifting downfield or more shifting upfield?
De-shielding.
It's de-shielding, right? And so again, here we've got very de-shielded protons. So anytime we have a structure like benzene, what we're going to find is the shift is going to be around 6.5 to 8.0 ppm. So we see some weird trends that we might not have expected when we have pi bonds involved. Yeah?
So for the de-shielding and shielding situation, is it the triple bond that causes this to happen?
Yeah, and so it's just the way that those p orbitals are in space that cause the molecules to line up the way that they do.
Okay.
Sarah?
But like, I don't get why acetylene couldn't just like turn over.
It just doesn't do it that way. It's just the way that the p orbitals and the pi bonds orient themselves in space. When we do this experiment, this is how they line up.
Is that true for acetylene or is it true for any triple bond?
It's going to be true for any triple bond. Now, of course, we could have molecules where we have other pi bonds. So those are going to be complicated cases, right? So we're just focusing on specific bonds in this case. Okay, so we see two effects, the inductive effect and then the anisotropic effect. So finally, we've got, let's see, we've got 17 minutes to do signals. I think we're on pace. I think we're going to be perfect. All right, so part D, signal splitting. Signal splitting gives us actually really useful information. And so let's talk about what that is. So we'll start out with a little nugget of info. We'll say that we don't always see one peak for each signal. Sometimes we can see multiple peaks for each signal. It's still one signal. The multiple peaks still represent that one signal, but sometimes we see multiple peaks. And so what we do is we call it splitting. And so we say sometimes a signal gets split. Okay, so everything we've seen up to this point has been what we refer to as a singlet. Why do you think we call it a singlet? There's a single peak, right? And so a singlet is a peak where it's just one peak. That's it. That's our singlet. But we can see cases where our singlet becomes a doublet. How many peaks do you think are in a doublet? Two. Very good. And so a doublet ends up looking kind of something like that. Now, how many signals is this? it's one signal, but we have a signal that's being split into a doublet, so we end up seeing two different peaks. All right, so after singlet and doublet, what do you think there might be?
Triplet.
Triplet. What letter do you think we abbreviate that to? T. Very good, Sarah. Okay, so what we end up seeing in a triplet is something like that, where our middle peak is about twice as long as our outside peak. And we'll talk about why that is in just a second. So after this, we can see a quartet, and ultimately a quintet. And really this keeps going, and you can see cases where there's a septet, an octet, a nonet, maybe? We won't go that far. So for a quartet, what we end up seeing is a picture where, again, they've got differing areas. So you can see the two peaks in the middle are twice as big. And then when we get to a quintet, it's actually going to look something kind of like this. And so we can explain why this is relatively easy. That's basically the rest of class is what we're going to explain. Why we see the different peak height or different peak areas in each of these signals being split. All right, so the question, why? Why do signals become split? Why do we end up seeing this, and how is it useful? Let's think of a molecule. All right, so our molecule, we'll put an ethyl group there to make these things an equivalent. So what we're going to have is we're going to have HA, or we're going to have HB. And so what we're going to focus on is just the signal of HA. So we're going to think about what would this signal look like on an NMR spectrum. Now, we know that to do this experiment, we're going to excite HA such that when HA is pulsed and is excited, we undergo a flip, right? So that's our alpha to beta exchange, and so we go with to against our magnetic field. Now, at the beginning, if this thing's just sitting in space, all right, there are two possible spin states, right? +1/2 and -1/2. And so we're in equilibrium. So for HA, it's about half +1/2 and about half -1/2 at the beginning. The same is true for HB. And so when we do this excitement right here, HB is already either spin state up or spin state down. So there's two possibilities for HB. Two possibilities. For that matter, there's two possibilities of HA, but that's the one we're doing the experiment on, so we don't have to worry too much of that, because we're going to blast that equilibrium into non-existence with our pulse. All right, so ultimately what this means is that HA can be an environment, or at least in a given molecule, it can be in an environment where HB is spin up, or it can be in an environment where HB is spin down. So ultimately, HA, when we do this pulse, how many environments are possible for HA? We've got two possibilities. Okay, so when we do our experiment, about half the molecules are going to see an HB that's spin up, and about half of the molecules are going to be where HB is spin down. And so ultimately, there really are two different environments for our HA. So let's write that down to say that there are two possible environments for HA. And so because there are two possible environments for HA, what we end up seeing is two peaks. Basically, our signal corresponding to HA has been split into two peaks because there's a neighboring nucleus that is going to give it a different environment based on whether it is spin up or spin down. So in this case, what we would see is a doublet for HA. It's a doublet because ultimately HA exists in two different environments because of that signal splitting caused by HB. All right, so let's look at another example of this. So our next molecule is going to look like this. So we'll still have HA, but now let's put two HBs here. Okay, so now that's our new molecule. And again, we're going to focus in on HA. That's what we're worried about. So as HA is excited, HB. So our HB equivalent. How many signals would we expect for HB? Do they have the same connectivity? Yes. Is there free bond rotation in this molecule? Yes. How many signals would we expect if we just consider HA and HB? We'd expect two signals, right? Because there's two sets of inequivalent protons. All right, so as HA is excited, when we consider HB, and when I say HB, we're talking about all the HBs because they are equivalent HBs. So we'd say that HB could be let's see, what are the possibilities? They could both be spin up. One could be spin up, spin down, or we could have the other case where we have spin down, spin up. And so what's the final possibility?
Spin down.
Both could be spin down. Okay, and so how many possible environments are there? Yeah, there's 4 maybe discrete environments, but between these two, we're not going to be able to tell a difference. It's going to be ultimately the same environment. So how many environments are there?
3.
There's 3 different environments. So because there's 3 different environments for HA, what kind of signal are we going to end up seeing? We're going to end up seeing a triplet. And so furthermore, because each of those signals, or each of those resulting split signals that we see, they have different likelihoods, right? It's a lot more likely that we're going to see this middle case. There's a 50% chance that we'll see that middle case, and then a 25% chance that we'll see either the top case or the bottom case. We end up seeing a signal where we don't have 3 equal peaks, but we find that the outside peaks are about half the area as the inside peak. And so it's because these are twice as much likely, right? Because there's 2 possibilities. And so you can imagine, as we get into more complex situations where we're being split differently, well, the math is going to become more complicated. And so we end up seeing different levels of peak area here. Now, there's an easy way to remember that, how we end up with our peaks. Who's familiar with Pascal's triangle? It's Pascal's triangle. That's all it is. All right, so let's remind ourselves what Pascal's triangle. So let's just say the peak intensity matches Pascal's triangle. So what that means is that at the top of the triangle, we've just got our singlet, right? And so that's just going to be, we can just call that the number 1. And so what's the second level of Pascal's triangle? 1 and 1. Does that look like a doublet that we've shown before? It does. That's our doublet. All right, so there we've got a doublet. Now, the next part of Pascal's triangle will have a 1 there. What do we have in the middle? 2, and then a 1 here. Does that look like the triplet we drew? Let's remind ourselves. Yes, that looks like the triplet we drew. And so ultimately, whether we have a singlet, doublet, triplet, on and on and on, it all corresponds to Pascal's triangle. And so as we go down, we see that, and then we'd see this, and so you can keep doing it all day, I guess, if you want to. If you're bored later, go ahead and just draw Pascal's triangles. Here we've got a quartet, quintet, sextet. So ultimately, those peak areas and a sextet, we know we're going to see 6 different peaks, and so each of those peaks, the area of the specific peaks, is going to correspond to just however Pascal's triangle works out. Because ultimately, what that does is it corresponds to the number of possible environments and then the overlaps between those environments. So, signal splitter. So why is this signal splitting useful then? What does it tell us if we see a signal that's split into a doublet? What does it mean there must be on a neighboring carbon? 1 other proton, right? It's split it into 2. What if we see a triplet? What does that mean it must be connected to? A carbon with 2 protons. And so this leads us to a very, very important rule, which we will refer to as the N+1 rule. And so the N+1 rule, we say that a hydrogen signal, or a proton signal, is split into N+1 peaks, where N equals the number of neighboring H's. Now when I say neighboring H's, do I mean H is on the same carbon or H is 1 carbon over? H is 1 carbon over, because if it's an H on the same carbon, well, those are going to be equivalent H's, right? And so those are ultimately the same proton that we're talking about. So we want to make sure we understand this is not connected to the same carbon. We're talking about 1 carbon over. All right, so let's do a quick example and call it the weekend. I saved it for the end, but today's my birthday, and so I'm excited to get out of here. How old am I?
That wasn't the joke.
How old do you think I am?
31. 35.
I turned 31 today. I heard a lot of people say that, so. All right, so let's look at the molecule.
I don't know.
What? I feel like people are talking. What's that?
You can make president when you're 35.
Thanks. All right, so in this molecule, we're going to go ahead and draw out all of our explicit protons. So, protons there, we'll have a proton there. A lot of protons here. This is actually going to be a carbonyl. Protons, and a lot of protons here. Okay, and so when we look at this molecule, the first question I want to ask is how many signals are we going to expect?
Up to you. I can't give you a number. I'm so ready.
All right, but they're not all. We're not going to see signals for each proton because we look for the equivalent protons. Where are we at? 1046. All right, we're okay. And so over here we have methyl groups on the end. Do they have all the same connectivity? Sure. And so we've got these things are all equivalent. This guy right here is kind of a lone wolf, right? Because he's the only one that looks like that. So then we can have these. Now, are these going to be the same as these? No, and so those are going to be separate signals.
And then the last guy in.
And then we've got a tert-butyl group, and there's one nice thing about tert-butyl groups. There might be a lot of protons, but are they all equivalent?
Yeah.
Sure, they are. And so I'm out of colors. We'll go yellow highlighter. All right, so how many signals do we expect? Yeah, we expect 5 signals, and so what we'll say is we have A, B, C, D, and E. 1, 2, 3, 4, 5. All right, so we have signals A, B, C, D, E, and so in terms of their the integration or the area of our peaks, we would expect a ratio of 6 to 1 to 2 to 2 to 9, right? And that just corresponds to the number of protons that are in each of these sets. So now let's think about splitting. Okay, so signal A, we're talking about our methyl protons. So to figure out what kind of splitting we would expect, all right, so we've got this carbon, we want to count one carbon over. How many protons are connected? 1. Is it the same case for these? They're equivalent. It has to be, right? And so what kind of splitting would we expect? We would expect to see a doublet for these 6 protons. Then what about signal B? All right, if we count over to hydrogen, here, how many are there? Here, how many are there? And so how many total is that? And so what kind of splitting would we expect to see? We would expect to see 7 peaks, a septet, right? Because n plus 1, there are 6 neighboring protons, and so we say 6 plus 1 is the number of peaks we expect to find. What about peak C?
Triplet.
Yeah, I hear triplet, and that's exactly right. So if we count 1 carbon to the left, we see it's a carbonyl, nothing there. If we count 1 carbon to the right, we see 2 protons, n plus 1. We would expect a triplet.
Do we ignore the carbons, like 2 carbons over?
Yep, it's only going to be the directly connected carbon in question.
So
The vicinal carbon.
the next one's triplet as well.
Yeah, so the next one would also be a triplet, right? Because there's nothing to the right, but we do have 2 protons to the left. And so finally, E with our big hulking 9 protons. What kind of signal would we end up seeing? Yeah. So we're going to end up seeing a singlet because for each of these cases, when we count the 1 carbon over, it's that one, and so that's a quaternary carbon. There's no protons attached, and so what's 0 plus 1? That is 1. We end up seeing a singlet. Okay, so you get lots of important information from signal splitting, and so we're going to basically do lots of practice on Monday. Have a great weekend.
Have a great birthday.
Thank you.
Oh my God. 3 exams and 2 essays and then 3 hours of sleep last night. It's been one hell of a week.